This video is going to focus on the first part of Ester enolates and the Claisen. The main thing in this chapter is going to be beta dicarbonyl compounds. Now remember, we've talked a little bit about alpha hydrogens, right? So the alpha position, alpha carbonyl, beta is going to be the next carbon over. So the Claisen condensation can take two esters, usually these are the same, and we're going to put them together so we have a beta carbonyl, right? So remember, our alpha carbons in between both of these, a carbonyl in the beta position for both of them. The chemistry for this should remind you a little bit of what we've seen before with the mechanisms involving our esters. So first thing, remember we talked about alpha hydrogens, alpha carbonyls being very acidic, and we're going to pull off one of those. Remember, in this case, since we're dealing with an ester, there's only going to be one position, so there's only one type of hydrogen that's going to be the most acidic. So we can pull off that hydrogen. I have both resonance structures here. The top one's going to become more important because it's going to act as an anion and a nucleophile towards another molecule of our ester. So it will add the nucleophilic addition, push electrons out onto the oxygen. This step should remind you a lot of our carboxylic acid chemistry. Electrons are going to push eventually back down to kick out our leaving group. But before we get there, make sure you can see here our tetrahedral intermediate, where we have the other piece of our ester at the carbonyl group. From here, you should see that we're going to push down and our ester group will leave. So elimination step, push those down, kick out our ester, and now we've added an extra 2 carbons and a carbonyl to the end of our ester. We'll have some extra base around. Up to this point, these are going to be reversible. You saw some of the arrows. It's not going to be entirely easy pulling off those hydrogens, but given time and heat, it will happen. The last part, what actually drives this mechanisms towards equilibrium, is that those alpha hydrogens that are between 2 carbonyls are going to be even more acidic than our traditional alpha hydrogens. You'll notice here that your base is also going to be the same as the ester portion. So if we have transesterification, or if this acts as a nucleophile at that position, it's not going to matter because what will get kicked out will be the identical molecule. So here, these will actually be resonance structures of the anion once that hydrogen is removed. Traditionally, there's acid workup at the end done in order to protonate it, and so we have our neutral compound. This is the same thing after step 3, but remember that with base around, those hydrogens are very acidic, so they are going to be easily removed. So we do need to have these last 2 steps. If we only have one alpha hydrogen, the Claisen reaction fails, and I'll show you the intermediate. This would be an example of having only one hydrogen, and since we don't have the ability to remove that hydrogen in step 4, since those first 3 steps are all reversible, we end up being pushed back towards our starting materials. So what we can do is, if we have a big molecule like this that we want to split into 2 esters, this will be a retroclaisen, so reverse. So a retroclaisen, we can break this up easily. Having this piece, remember, since there's no acidic hydrogen between the 2 beta carbonyls, our base can act as a nucleophile, pushing electrons out. Now this can push down, kicking out our large leaving group, and now we will have 2 molecules of our ester after protonation. If you want to do a mixed Claisen, it's going to involve having 2 different types of starting materials. Traditionally, one is chosen with having no alpha hydrogens, so you know that that one has to have a nucleophile. If you have 2 that have both available alpha hydrogens, you will get a product mixture of several different products. But here we can see that our benzene ring on the left has no alpha hydrogens. That's going to act as a nucleophile. We're going to pull off our hydrogen from our alpha carbon on our ethyl ester, and we'll have that new carbon-carbon bond between the carbonyl on our benzene ring and the alpha carbon of our ester. You can also undergo an intramolecular Claisen, otherwise known as a Deichmann condensation, where the same chemistry happens. It's symmetrical, so it doesn't matter which alpha hydrogen you take, but we'll end up closing the ring. Keep track of your carbons here. It is not the carbon in the carbonyl. It is your alpha carbon, either one, that's going to end up acting as your nucleophile, so you should end up seeing a 6-membered ring, not a 7-membered ring. You can have ketones that also undergo reactions. Remember, these protons are going to be a little bit more acidic, so we know that that carbon is the one that's going to lose its alpha hydrogen, not our ester. Also don't have a good leaving group on our ketones, so that would not act as a source of as an electrophile. If you want to use Claisen in the syntheses, these are your 4 things to remember. Your product is always going to end up being a 1,3-dicarbonyl compound. One of them needs to be an ester. The other one must contain at least 2 hydrogens on the alpha carbon. If you're doing a mix, meaning that you're using 2 different starting materials, make sure one has no alpha hydrogens, or your product mixture can get pretty messy. So if we look at this molecule on the bottom, in order to make this compound, we can make one of 2 bonds. We can have this bond be made, or we can connect this bond. So look at those 2 options. If we connect on bond A, we're going to have a 1 starting material with an intramolecular Claisen or a Deichmann condensation. This is a very long molecule, and the likelihood of getting it to do our Claisen the way we want it in the structure is a little bit low. So if you have 2 smaller sets of starting materials rather than 1 large one. So your best bet to make the above molecule would be something like this, where we have a ketone where we have an alpha position that would be symmetrical on either side, and we have an ester without any alpha hydrogens, so we can have our ketone act as our nucleophile and eventually give us our dicarbonyl compound. That's it for this video.